In this video, we're going to pick back up with Lecture 3, and we'll be focusing on ionization energy. We talked some about ionization energy when we talked about PES, that photoelectron spectroscopy, and we looked at how much energy it would take to knock off an electron from different elements. So we should have an idea already of the sort of trend in the ionization energy. The ionization energy is, by definition, the minimum amount of energy that is required to remove the least tightly held electron from an atom or an ion in the gas phase. So the way that we define this, we have to be specific about when we're taking this electron off, because in different states it would take different energy. So by definition, the element needs to be in the gas phase. And for the first ionization energy, which is what we're talking about on this slide, so for the first ionization energy, we're removing the least tightly held electron. This always takes energy. So these values for ionization energy are always positive to indicate that energy is being put in to make this happen. The trend in ionization energy is that the ionization energy generally increases as we move from left to right on the periodic table. And that reason, just like for atomic size, is because we're adding more protons to the same energy level. So if we're thinking about Coulomb's law, that's going to increase the charge, which thereby increases the attractive force. If we are looking up and down on the periodic table, the ionization energy increases as we move up the periodic table. And this is because as you move up, you reduce the energy level of your valence electron. So that's reducing your distance. So if we think about Coulomb's law, we know that distance squared is in the denominator. So if the distance decreases, then the force of attraction is going to increase, making that electron more difficult to remove. Here is a chart showing the first ionization energy for several elements as we move, starting from element 1 on the periodic table and moving down. So you have element 1, hydrogen, and then helium, increasing as we go across. Then lithium, decrease as we go down. Then we go across, down, across, down, across, so on and so forth. But you'll see some exceptions here, which is what we want to focus on at first. So we have this beryllium-boron exception. Then we have an exception here as we move to aluminum, an exception here as we move to gallium, an exception here as we move to indium. So what do these elements have in common? Beryllium to boron, so boron is an exception, aluminum is an exception, gallium is an exception, indium is an exception. If you look on your periodic table, these elements are the first element in the P block within each row or period, and they are an exception to this ionization energy trend. And so we'll look at the reason why. So in general, the ionization energy increases as your radius decreases. Okay, in general. So it's opposite of the radius trend. So as we go across, radius decreases, ionization energy increases. As we go down, radius increases, ionization energy decreases. Why? Because the force of attraction decreases as your distance increases, according to Coulomb's law. So according to the law, if the particles are further apart, there's less attractive force, so it's easier to remove the electron. However, we see a few exceptions. One exception is when we move into the P. Okay, so I want to ignore this right here, and we're talking about the P sublevel. It's going to require more energy to pull an electron from the S than it does from the P. Okay, why? Because the P, being in that separate subshell, is slightly higher in energy, only slightly, and is therefore shielded by the electrons in the s sublevel. So the electrons in the s sublevel are a little closer to the nucleus, so they're harder to remove. But in the p sublevel, they're a little further from the nucleus. It's a little higher energy sublevel, so therefore easier to remove. Only in the same period. Okay, so in the same period, that p is going to be easier to remove than an s, just the first p, because it's a little further from the nucleus than those in the s sublevel. Now once you're in the p sublevel, now you're adding protons in that same sublevel, so it's going to get increasingly difficult to remove the electron. But just when you make that jump into the p, that first electron in the p sublevel is a little easier to remove because it is further from the nucleus. Alright, I'm going to switch to a PowerPoint, and I can send you these pictures as needed if you'll just remind me. But I wanted to make a little bit more sense of ionization energy using some pictures. So on this PowerPoint, we're going to look at, first of all, we're going to just talk about ionization energy again, and just in terms of these pictures so we get an idea of what's happening. So the first ionization energy is the energy required to remove the least tightly held electron from a gaseous atom. So I have lithium, sodium, and potassium, and we're using the Bohr models. Now, we know that the Bohr model is somewhat inaccurate, but it does give us an idea of how far the electron is from the nucleus. So on lithium, we would be removing this electron. On sodium, we would be removing this electron. And on potassium, we would be removing this electron. You can see the ionization energy is less for sodium and even less for potassium. And these are in the same column. So lithium, sodium, potassium, we're moving down the periodic table. The ionization energy is decreasing because that electron on the outside is further from the nucleus. And according to Coulomb's law, if the distance goes up, the force of attraction holding that electron on there is going to go down. So it's going to be easier and easier to remove an electron. It's going to take less and less energy. Now what I want us to look at, though, is what about if we want to keep taking electrons off of an element. So over here on the right-hand side, you see a Bohr model for silicon. So you have 2 inner shell electrons, because there's 2 elements on the first row, 8 on the second, and then 4 on the third. So let's think about just removing these electrons from silicon. So the first 4, which you see in green, and then they're over here on the graph, they are taking about the same energy to remove. So the first one would be the easiest to remove, and then the next 1, 2, 3 are increasingly difficult, but still within the same range. Those are the furthest from the nucleus, so they're the easiest electrons to remove. Notice, though, when we get rid of those 4 and we try to remove a 5th, notice this huge jump right here. This huge jump is indicating to us that we're going closer to the nucleus, that we're on a different shell. And then we see, once we get to that shell, those are similar, still increasing, but still similar in their ionization energy because they're all coming from the same row. Then finally, if we get rid of those 8 and we try to take these that are very, very close to the nucleus, that's going to take a ton more energy. Okay, so the ones that are furthest from the nucleus we see are all kind of similar, but it does increase, and then we see a big jump as we go closer to the nucleus. Okay, now looking at that for aluminum, you see aluminum as a neutral atom is very large, and then we take off an electron that takes 578 kilojoules of energy, and then we try to take off another electron. Now the atom's smaller, so that's going to take more energy, and that makes the atom even smaller, so to remove another electron would take even more energy. So the subsequent, after the first, the subsequent ionization energies are always higher because the electrons are being held more and more and more tightly. However, looking specifically at aluminum, once we get rid of those three, so if you can focus right here on this line, you see the energy to remove the first one, the energy to remove the second one, the energy to remove the third one. Okay, that's what we just looked at on the previous slide. So about 500 or 600 if we're rounding, then 1800, then 3000 approximately to take off this 1, 2, 3 electrons. But then if you try to take off the fourth electron, look at this huge jump from the third to the fourth. Why is that fourth electron so difficult to remove compared to the third? Because the fourth electron is on an inner shell. So looking at this data, we get an idea of how many valence or outer electrons these atoms have. For example, sodium has only one valence. So when we go from the first ionization energy to the second, it's almost 10 times as difficult because the second is from an inner shell. Magnesium has 2 valence, so we kind of double from 1 to 2, but then from 2 to 3, look at that huge jump, because the third is in an inner shell. So however many electrons you have before the huge jump is telling you how many valence electrons there are within that element. Let's flip back to your notes and then we'll come back and look at some more examples. Alright, so picking up on your notes, this kind of summarizes what we were saying. The second ionization energy is always greater than the first, and the third is always greater than the second, and the fourth is always greater, and so on and so forth. Because when you remove an electron, you reduce the radius. So the ratio of protons, your positive charge, to your negative charge is now greater, and those electrons are going to be pulled in tighter. So the second one's going to be harder to remove, then they'll pull in even tighter, third one's harder to remove, etc. However, every element has one extremely large increase in the ionization energy, and that occurs when you're dropping that principal quantum number. Okay, another way to say that is when you're dropping energy levels. That is causing your radius to shrink much more than if you're just losing an electron on the outer shell and you still have some left. So you got one extremely large increase because you're moving down a shell, not just a sublevel, but a whole shell. So you're moving from like the third energy level to the second. And they use this term principal quantum number, and that's just referring to your energy level. So you're dropping, let's add here, an energy level. Sorry, it's hard to write with this marker, but you get the idea. Energy level is the same thing as this principal quantum number. All right, let's go back and look at some more images of that. Still talking about aluminum here, this is just another way to represent that. And so you see the first, the second, and the third ionization energy. While it's steadily increasing, these are all within the same range. And then we see a big jump to take off the fourth electron because it is in an inner shell. While these down here are our valence. Okay, so you see the difference there. Then these all increase in difficulty as well. Go back up here. Okay. These are still steadily increasing, steadily increasing because as you remove each one, your atom gets smaller and smaller and smaller. But you're going to see a big jump when you move into an inner shell. All right, let's look at chlorine. Okay, so this graph here is for chlorine. We have the 3p electrons down here. It has 5, 3p, and then the 3s. This is not really important in terms of where they're located, p or s, just that these are all in the third energy shell. So you have 7 valence electrons for chlorine, but you try to take off that 8th electron, that's coming from an inner shell. It's actually coming from the 2p. So you have, for chlorine, the arrangement is 1s2, I'm not going to do exponents, but 2s2, 2p6, 3s2, 3p5. So these 7 electrons that are in the p5 and the s2 on the third energy level, those all come off relatively easily, but if you want an 8th electron, you've got to get it from the second energy level, and that's what's going to take so much more energy. Okay, another example, we don't know what element this is, so we're going to try to make a guess. The first electron, relatively easy. Second electron, still in that same range, but you try to get a third electron, it's going to be so difficult. So what elements would it be really difficult to remove their third electron? This would be elements in which they have 2 valence electrons. So what elements have 2 valence electrons? Those are elements in group 2. Right? So that could be a multiple choice question, and they could ask you what element does this represent. So it'd have to be an element from group 2. You see that they've already removed like 12 electrons from this element, so it can't be something like beryllium, which only has 4 electrons. But it'll be something from group 2. Right, here's another question that could be asked involving ionization energy. This has the table of the successive ionization energies for some element Q. They often use Q to represent an unknown element. So you see Q's first ionization energy is given there as 418, and then there is a huge jump to 3,000 when you try to remove the second. So what is that telling us? It's telling us that if the second electron is that difficult to remove, it must be from an inner shell. So this element must only have 1 valence. Alright, so let's go back to the question. What would be the likely formula of the oxide of Q? That means when Q joins with oxygen, what would the formula be? Well, if Q has 1 valence, what charge do you think it's going to have? If it only has 1 valence, it's going to lose that 1 valence to be +1. Now, oxygen, we know, wants to gain 2 electrons, so it's going to be -2. So put them together, and the formula would be Q2O. Sorry about that line through the O, but Q2O would be the likely formula. Okay, hopefully that makes sense. All right, back on your notes, just really quickly, we'll talk about electronegativity. The definition is an element's ability to attract electrons, and here's the key, in a chemical bond. So what happens is you put 2 elements together, and then you see their shared electrons, so they're making a bond, which are shared electrons. Where are those electrons spending most of the time? If they're spending most of the time around one element versus the other one, they're not really being shared evenly. Then that element that they're spending the more time around is the more electronegative. Okay, so that is written there below. The electrons spend more time around the more electronegative element in that bond. The basic trend is the same as the ionization energy. So electronegativity increases as we move across and decreases down or increases up. That can be stated either way. This is key to remember. These noble gases have no electronegativity values simply because they don't often form chemical bonds. We will see them form chemical bonds, but not often enough, and so they don't measure their electronegativity values. The most electronegative element, therefore, is fluorine. It's the most, and then francium down here being the least electronegative. All right, so why is that? Well, you can see that it's opposite of the atomic radius trend. So the electronegativity increases as the radius decreases. Because when two atoms are in a bond, if the atom's big, then those electrons are going to be further away from the opposite nucleus. But if the atom is small, the electrons can get closer to the nucleus. And again, according to Coulomb's law, this is going to be the key to everything, if the distance goes up, the atoms are big, the electrons can't get as close, then the force is going to go down. That force of attraction, which is what electronegativity is. The force of attraction for another element's electrons.